All right, guys, so we've talked about each of our points of concurrency now, and on 57, I want to do some like mathematical practice with that. So if you turn to page 56 and 57, on 56, we tried out all of our special lines or line segments or rays that we can draw. But then when I draw like all three of the perpendicular bisectors, I get a circumcenter. So we get all these different centers now, and they also have like a super fun mathy fact about them. So on page 57, we want to do a practice with that. Now again, what I would recommend, just like I did with page 56, is I would go through and try at least the front out, and then maybe come back and then try the middle out, and then come back and check your answers. So I would try it out first, see how you do, and then come back and you can hear why something is the way that it is, and you can see if you are really getting it or not. So in each figure below, tell what point of concurrency is shown and what constructions would form that point. So here, I actually like to do it in the reverse order. So like I like to identify the lines being drawn, and then that tells me which point of concurrency I have. Excuse me. Oh my God, gross. So here I can tell that all of the altitudes were drawn, and I know that they're altitudes because they are perpendicular and connected to an angle, and they're not bisectors. So these are altitudes, and when all three altitudes are drawn, they form the orthocenter. Now on this one here, I notice that the lines that are drawn are all medians, and I can tell that they are medians because it is a middle connected to an angle opposite. It's not perpendicular, so it's not a perpendicular bisector, and the angle wasn't cut in half, so it's not an angle bisector. When all the medians intersect each other, they form the point called the centroid. Next, these lines I can tell are perpendicular bisectors because I notice the 90 and then the side is cut in half, so perpendicular bisector. And when the three perpendicular bisectors of a triangle are all drawn, they always intersect, and we call that point the circumcenter. And lastly, I mean, it makes sense, it'd be the one that's left, but I can tell that these are the angle bisectors because of the rainbows. And when I draw all three when I draw all three angle bisectors, they will always intersect, and I always call that point the incenter. So then we just want to think about other ways that we can talk about these centers. So which point of concurrency are always inside the triangle? So the incenter will always be inside, no matter what type of triangle I have. Also, the centroid will always be inside. Sometimes the orthocenter and circumcenter can be outside if it's obtuse, or right on the triangle if it's a right triangle. Which point of concurrency is always on the vertex of a right triangle? So I just said that the circumcenter orthocenter could be right on the triangle if it's right. Now the circumcenter ends up on the hypotenuse. The orthocenter will be on the right angle. So then I think that answers this next one. Which point of concurrency is always on the midpoint of the hypotenuse? That would be a circumcenter. Which points of concurrency are always outside of an obtuse? That's our ortho and circumcenter. Again, if the incenter and centroid always have to be inside, can't be those. Which point of concurrency is the center of gravity? Oh, I kind of want to go grab this. I'm going to go grab it. That is the centroid. I don't think it'll be hard to find. Oh my gosh, you can hit pause and come back. This will take 2 seconds. I'm so sorry. I could edit that out, but I just don't want to ruin the video. Okay, so I have this cardboard triangle here. You can maybe see all of our points of concurrency are drawn on it. Specifically, this one right here is the centroid. If I put my finger on that, and I don't have nails, and the triangle isn't bent, the triangle will balance on that point. I promise you my finger is on it. But if I put my finger anywhere else, the triangle is just like falling off. So if I try to put it on any other center, like you can see, the circumcenter is going to be way too low. So neat. So the centroid is our center of gravity. Which point of concurrency is equidistant from each vertex? So that was the one that had the circle going through all the angles or on the outside of the triangle, and that is your circumcenter. The incenter is equidistant from the sides because that's the one inside the triangle touching all the sides of your triangle. Alrighty. So along the side here, name the point of concurrency. Well, this one, I noticed there are perpendiculars, but it's not a bisector because it's not showing me that it's bisected. What it is showing me is that this point is equidistant to all the sides, and the incenter is that. This one is real weird because it's like a line from an angle to a point. And furthermore, they're showing me that from an angle to a point is equidistant. And the circumcenter does that because the circumcenter is the one that has a circle drawn on the outside. So it's crossing through all the angles of your triangle. And then lastly, this one here, it's showing me that my point of concurrency is outside the triangle. So that narrows it down a bit. It could be a circumcenter or it could be an orthocenter because this triangle is obtuse. And I think it's going to be the ortho because these are not perpendicular bisectors. They are perpendicular, so that makes them just altitudes. So orthocenter. So those are kind of unique ones because it doesn't show, well, this one shows the altitudes, but these two don't show the special line segment that you've drawn, which you don't really need to. Now, we need to talk about the centroid because the centroid has this sort of unique math fact about it. Not only is it the center of gravity, but also it has this 2-to-1 ratio going on with its sides, and this printed really badly. But if we know that AD is 8, AG is 10, and CD, this whole line here, is 18. That can be super helpful to figuring out a bunch of other sides. In fact, I'm going to label all the things that I can label in my triangle first, and then I'll go answer these questions. Now, because this is the centroid, these are the medians. And so if this is 8, so is this, because D would be at the midpoint. Now again, if I know part of the median, then I know it has a relationship of 2-to-1. So when I have this median drawn here that the 10 is on the larger portion, which is 2 times as much as the smaller portion. So this would have to be 5. Now the tricky part is though, if I know the entire line, then really what I have are 3 equal parts because this has 1 part and this has 2 parts. Like there's 1 5 here and 2 5s there for a total of 3 5s. So really there are 3 equal numbers on here. 1 of them goes here and 2 of them go there. So I really need to split the entire line by 3. And so that would give a 6, a 6, and a 6, where 1 of the 6 goes on the small part and 2 of the 6s go on the large part for 12. And that's really all I can find because those are the only numbers that they gave to me, so hopefully it's enough. So BD, yep, that was 8. AB, that'd be the whole thing, so 16. EG, that was 5, that was half of the 10. AE, the whole thing, 15. Oh, and I can also see it there, so 15, if I split it in 3, that's 5, 5, 5, so 10, so 15 for the whole line. CG is the longer part, so 12, and DG is the smaller part, so 6. So when they tell me the whole line, I always like to find the smaller part first, even if I don't need to, because then I can just always double that to get the longer. All right, jumping down here. This guy, so I can tell that they have the angle bisectors here, which means where they cross is the incenter. And the incenter is equidistant to the sides. So I can set x plus 9 equal to 3x plus 5 and solve for x. So subtract 5. So 4 equals 2x. So x is 2, which would make this 11 and that 11. So that's good. Similarly here, we got those angle bisectors. So this guy where they cross each other is the incenter, and the incenter is equidistant to the sides. So again, I can do 2x plus 2 equals x plus 13. Subtract the x, subtract the 2. So x is 11. So this would be 24. And so would that, if I plug it in. Oh my gosh, same deal. I have the angle bisectors, and where they cross each other will be the incenter. And so the incenter is equidistant to the sides. And guys, really long story short, like in this chapter, either stuff is equal or maybe it's like double or half. And so you can kind of base it on like what they look like. Like these two little line segments, they look equal. So I'm going to set them equal. The 5 didn't look the same length as the 10. So I shouldn't say that it's also 10. I should take half. And like, if that's your choice, like you either have to take half or they're equal, I feel like that makes all this math pretty simple. So we get x equals 3 here, meaning this is 6 and that's 6. Now with these ones, we want to name the point of concurrency. So again, I can tell that all of these are angle bisectors, so they're all incenters, but I need to figure out which point is the incenter. So I really find it helpful to kind of trace out my angle bisectors and see where they cross each other. So they're crossing right there, which is what Q is pointing to. So Q is the incenter. Similarly here, if I trace out this angle bisector and that angle bisector, they meet at U. So U would be the incenter. And then lastly here, if I trace out this angle bisector coming out from the angle, they meet at X. And so X is my incenter. And I think that's it. So hopefully that went okay.